Hi everyone. Today let's talk about some properties of odd and even functions and how that can help us in our calculation for a sub n and b sub n in our Fourier series. So let's start with odd functions. So odd functions have a very important property that f of the opposite of x is equal to the opposite of f of x. And if we want to think of some examples of odd functions would be f of x is equal to x cubed, or f of x would more generally be equal to x sub n, where n is odd. Or we could say f of x is equal to sine of x. Or we could also say f of x is equal to sinh of x. All of these are examples of odd functions. And what do they have in common? Well, the thing that they have in common is that their graph is symmetric about the origin. So if we look at a graph of, let's say, x cubed, if we look at the graph of x cubed, it looks something like this. X, f of x, this is y equals x cubed. So we see that this graph is symmetric about the origin. And another way to think about it that our professor mentioned in class is that you could stick and spin. So you pick this point right here and you spin this 180 degrees, and it's gonna be in the same position in the third quadrant. So this is an example of an odd function, or another example would be the sine function that looks something like this. So you see that the sine function has a point here at the origin, and it has its maximum value of 1 at pi over 2. And you can kind of see this graph right here. So if we think about it the same way, if we stick a pin here at the origin and you slide it, you rotate it 180 degrees, you can see that it's going to be in the same position as this other part. So it's symmetric about the origin. So this is the property that odd functions have. So it's important to highlight this relationship right here is one thing that you need to remember. And it's also important to remember that odd functions are symmetric about the origin. So this is also important to remember. One more thing. So let's look at this graph, and if I ask myself, what is the integral from negative pi to pi? What is the integral from negative pi to pi of sine of x? Well, if you want to do it, you could just integrate it and see that the integral of this would be negative cosine of x from negative pi to pi, and you could check that this is going to be equal to 0. But another way that you could see is from symmetry. Even though my graph isn't drawn to scale, you could see that this negative area, and I say negative in quotes because an area is always positive, but you see that there's this positive region and this negative region, and when you take the integral over over like a symmetric interval, so negative pi to pi, we can see that these regions are going to cancel out. So the integral is going to be 0. But you could write that more generally. You could say that an integral over a symmetric interval, negative L to L, of an odd function dx, or whatever your variable of integration is equal to 0. So that is like a fundamental property that is worth remembering. So these two are worth remembering, but this one especially, because it's going to be very useful in our calculations. Okay, let's talk about even functions now. So even functions, So the fundamental property of even functions is that f of the opposite of x is equal to f of x. That is a really important relationship that we need to remember. And what are some examples of even functions? So some examples would be f of x is equal to x squared, f of x is equal to x to the n, where n is even. This is more generally. Or we could say f of x is equal to the cosine of x, or f of x is equal to cosh of x. All these are examples of even functions. And what do we need to know about even functions? What is similar about their graphs? Well, even functions are symmetric about the y-axis. So this is important as well. So what are examples of even functions? Well, so if we draw a graph of the odd function, let's say the first example, f of x equals x squared. Whoops, my pen. There you go. It would look something like this. Y equals x squared. So the way to think about even functions is, if you have a value x naught in the positive direction, we're gonna have a corresponding value f of x naught. Correct? But if we go the same distance the other way and get a value f of negative x naught, we need to get, if my parabola was drawn correctly, more to scale, we needed to get the same f of x naught. So this is how you think of it. It has to be symmetric over the y-axis. Another way to think about it is that if you pick the first quadrant and the fourth quadrant here, and you kind of like flipped it, if you like fold it in half here about the y-axis, they would have to lie on the same parabola, on the same line. So this is one way to think about it. Or we could talk about a trigonometric function as well. Let's talk about cosine of x. So the graph of cosine of x looks something like this. Even though I'm not an artist, but you can kind of see the point. So this is the graph of cosine of x. You see here any point, like if you can flip this graph in relationship to the y-axis, and you're going to get the same graph in the other side. So it's symmetric about this y-axis. And an important relationship about even functions is that integral from negative L to L over symmetric integral of an even function dx, or whatever your differential is equal to twice the integral from 0 to L of that even function with the same differential. So this is the important relationship about even functions. Even, and this one is for odd functions. These two properties here helps out a lot when we're doing our calculations for a sub n and b sub n. So it's really important to have those in mind. And the last thing I want to say in this video, is that an odd function times an odd function gives you an even function. And an odd function times an even function gives you an odd function. And an even function times an even function gives you an even function. So these are also important to remember because many times we're going to be multiplying, for example, let me erase this part over here. So many times we're going to be multiplying, we're going to be doing the integral of an odd function times an even function, you know? And it's important to realize that the product of an odd function and an even function gives you an odd function. So the integral of that over a symmetric interval is 0. So it's useful. One way of not having to memorize all of these things that particularly works for me because I don't like memorizing these things. When I'm in a test or a quiz, when I need to remember, oh, what is the product of two odd functions? Well, just think of two odd functions at the top of your head. If their product, if you think about x cubed times x to the 5th is x to the 8th, we see that a product of an odd function and an odd function is an even function. So there you go. You don't need to memorize the results. You can just think of functions in your head and multiply them out. What about an odd function times an even function? So let's pick an odd function x cubed, and let's pick an even function x squared. So when you multiply this out, you add the exponents, and you're going to get x to the 5th, which is an odd function. And here, our last example, let's pick an even function, x to the 4th, and another even function, x to the 4th. And you multiply them out. So when you multiply these, you add the exponents, so you're going to get x to the 8th, which is an even function. So I usually don't memorize the results. This is how I think of it. Might be helpful to you. Alright guys, that's all I have for today. I'll see you next time.